Yeah, I'll just announce once that they can go to the council room. Hello everyone. Those of you who are standing, there is another room that we are doing a Zoom telecast of the same talk. There are few seats. Sorry. So there's a Zoom telecast of the same talk that is happening outside. So if you go straight, take a left, there'll be a council room. So in case those who are standing, if they wish, they can go there as well.
Please, ಇನ್ನೊಂದು ರೂಮಲ್ಲಿ ಸೇಮ್ ಟಾಕ್ ಟೆನ್ನಿಸ್ ಕಾರ್ಡ್ ಆಗ್ತಾ ಇದೆ. ಅಲ್ಲಿ ಹೋಗಿ ನಿಂತ್ಕೊಳ್ಳೋ ಬದಲು ಅಲ್ಲಿ 1 hour ಆಗುತ್ತೆ ನಿಂತ್ಕೊಳ್ಳೋದ್ರೆ ಕಾಲ್ ನೋವುತ್ತಲ್ಲ. ಪ್ಲೀಸ್ ಪಕ್ಕದ ರೂಮಲ್ಲಿ ನಡೀತಾ ಇದೆ ಸೇಮ್ ಟಾಕ್. ಸಸ್ತಿಕ್ ಅಲ್ಲೇ ಕುತ್ಕೋಬಹುದು ಹೋಗಿ.
We love to see all of you, but I know this is difficult. We are going to live stream this also in the Pandal. There's more space there. So if you don't want to stand, please go to the Pandal and you can sit there and listen. Okay, there are chairs, there's a nice lawn. If you're happy to stand, that's fine. But you have to give us a few minutes to make sure that the setup is there. We already exhausted our floor space. There are a few minutes, let the setup be done, then we'll start. Okay. But if you don't want to stand, please you go to the Pandal and sit. We're live streaming the thing on a TV then. Okay. So we'll wait for a few minutes. Till then, you can just ask him questions informally. You know, if you have a blackboard was in front of you, why are you not making use of it?
Yeah, please be welcome to ask any question if you have in mind. Yeah, but don't ask what is the black hole shadow because that is the top.
Sir, how is the black hole form?
Yeah, so I'll actually discuss that in my talk. It is basically forms when a star dies. Okay, it forms at the end of the lifetime of a star. So I'll show that in my talk. What is your name?
Samadashan. Sir,
Yeah, can you say your name first?
black hole is there.
Name your name.
My name is Nila.
Okay.
Black hole is there, like that white hole is there.
So white hole is also a solution of Einstein's theory of general relativity, but we have not seen it yet. Okay, so we don't know whether it exists or not.
Sir, my name is Nilika. I'm here to ask what is the biggest black hole in the universe? I know the biggest black hole in the galaxy though.
Okay, so the biggest black holes are basically sitting now at the center of very large galaxies,
Yes, spiral galaxies.
spiral galaxies or even elliptical galaxies. So they are actually very large in size, okay, and they have a huge mass. So they basically weigh about billion times the mass of our own sun. So they are very large. Yeah.
Is there any name for them?
Supermassive black holes.
Oh, yeah. Thank you.
You can give it to him.
By the time a star dies, do you mean it explodes or what happens to it?
Yeah, so sometimes it explodes. So depending on the size of the star and what are the processes inside the star, the explosion may be very big or it may be small.
I see. And if the explosion is big, it becomes a black hole.
So that depends on the mass of the star. If the mass is beyond a certain number, then it becomes a black hole. If not, then it becomes something else.
Thank you. Are all the black holes originated from stars?
Okay, so that's a very good question. So the smaller ones, which are of the order of, let's say, solar masses, or masses which are comparable to the masses of the sun or a little bit larger, they are formed due to the death of the stars. But the black holes which are there at the center of the galaxies, it is still basically an open problem. So there are different theories which says how they form. So it could be like there is some small seed black hole which formed due to the death of some star, and then maybe there is a lot of mass or gas or dust which basically fell in, and that grew into a supermassive black hole. But the other way is it could have been formed when the universe was born. Okay. So due to some fluctuations at the beginning of the universe, some small black hole could have formed and that could have grown eventually. So this is still an open problem.
So I have one more question.
Okay.
So the thing is, if a black hole dies, then does it form a white hole to emit out all the things it sucked in? Because in a video, I saw that a white hole lasted for only 2 minutes.
Okay, so was it a YouTube video? Yeah. So you shouldn't believe everything that you see on YouTube, first of all. Okay. But to answer this,
It also,
yeah.
it came through in Google.
Okay. So basically, first of all, what do you mean by what is the depth of a black hole? Okay, so
Means like when a black hole cannot suck anything more, it then collapses. Then I searched in Google what happens. So then it told it will emerge out in white in color and emit out all the things it sucked in. Is that true?
So that is not completely true. So when a black hole is basically formed, and even if it can grab more material, eat more material, or if it cannot, it still emits some kind of radiation, which is called as Hawking radiation. Okay, through which it can lose energy and mass. So through that process, it becomes smaller and smaller. So it doesn't die, it basically evaporates. Okay, but what happens at the end of the evaporation is another open question. So we really don't know what happens when the black hole really becomes in a very small size. Okay, will it continue to radiate further, or what would happen? That is still an open problem. Okay, and white holes have not been observed in our universe yet.
Okay, we'll take short questions maybe. Yeah.
What about this side?
This side. Okay, we'll come.
He has already asked.
Sir, I have one more question. Does black holes have width or weight any?
So they have a mass. So if you can put a black hole on a weighing scale, it will basically show some weight, but that is not possible. So they have mass.
Yeah.
If can scientists find out if like where do things in black holes go to, and even if they do, how do they find that out?
Okay. So once anything goes inside that black hole, it has to go and reach a point called as the singularity, which is basically the central point of the black hole. Okay, so all the mass of the black hole, whatever form the black hole, it basically goes and sits at the singularity. So that is another open problem in general relativity. So we don't know how to describe a singularity. So that's a point where basically your energy density or mass density becomes infinite because point has no volume. Okay, so basically the theory of general relativity, it breaks. It cannot answer questions what happens at the singularity. So what we should know is how to describe processes in the presence of quantum mechanics. So quantum mechanics describes things which are very small. So now you have a region where gravity is also very strong and the size is also very small. So you need to basically use both the theories together. Okay, so you need to know what is quantum gravity. You don't know what is the theory of quantum gravity. So this question is still unanswered. So you guys have directly reached to the end of my talk. You are asking the questions which should have generally been at the end of the talk. Yeah.
So down the black hole substance stuff, it will fill itself and like let's say something like will it be possible to and then it will that happen?
So whatever globe goes close to
I interrupt again. We cannot comment. We don't want to stand for the Pandal. A few chairs in the council room. You are going to sit there in one room. Is everybody here who's standing want to stand here only? Yes. Sure. For the whole 1.5 hours. No complaining afterwards. Okay, fine. Some of you can sit in the middle also. Nah? Then I going to eat.
Yeah, you can sit down.
Some of the kids can sit in the middle. But no more people are coming in. We are not getting any more people. Whatever they want.
We'll come to the questions, yes, and yeah, please not now. After we take the questions, then we see in the middle because then we cannot move along and then take the questions. Please cooperate. Once the talk starts, we'll see. Once the talk starts, please cooperate now. While the question and session, once it goes over, we'll see the middle. All right. Yeah, so good. And also, please be silent. We'll try to take as much questions as possible. Please be patient. Yeah.
Yeah. So let me recall what you asked. You asked whether a black hole can.
So what if the black hole sucks up everything in the world? Will it later release it back?
So basically, it will need only those things which come close to it. Okay, things which are already far from the black hole, they will not be affected by the black hole. Okay, so it will not like eat everything in the whole universe.
What's the difference between a black hole and a Boson star? Boson star.
Okay. So a star is basically made up of bosons. Okay, so those are different kind of particles. Okay, they are basically of spin 1. Bosons. Okay, integer spin particles. Okay, these are basically called as boson particles. So any star which is made up of those particles would be boson stars. Okay, and black hole is a different quantity, which I'll basically explain like what is a black hole in my part.
There's a fire safety issue. Please do remember, we're letting you here stand here, but it's not a good idea. If some of you would like to shift to the bazaar, it'll be really nice. You can always come back at the end to ask questions. Nobody will let you ask questions in the middle of the talk, so you can come back to ask them later if you want to. That'll be good for you. It'll be comfortable. So please do think of it.
So I have heard that even light cannot escape a black hole, even though light is faster than anything which is formed by scientists on Earth. Why is that so?
So that is how a black hole is defined. Like it has such a strong gravity that even light, which is the fastest particle, is basically sucked in. So if light cannot escape, nothing else can. Okay, so that is one of the definitions of a black hole.
I know that there are also rotating black holes. So, if singularity is a singular point, how does singularity rotate in rotating black holes?
Okay, so basically singularity is different for rotating black holes. There are different kind of singularities. So depending on what is the black hole that you are talking about, if it's not a rotating black hole, a black hole which just has mass, okay, a spherically symmetric black hole, then the singularity is a point singularity. Okay, but if it's a rotating black hole, then the singularity has a different nature. It's basically a ring singularity. Okay.
Yeah.
How big is the biggest black hole and what is its name?
Okay, so maybe the biggest black hole is yet to be found. But like I said, every large galaxy will basically have a supermassive black hole at its center. So if we continue to find larger and larger galaxies, let's say even far off, I mean, you would have figured out what is the next big black hole.
How does the black hole get its gravity?
From the star which collapsed. So it formed due to the death of the star. So the star had gravity to begin with, right? So the material which collapsed there in the star, that provides the gravity.
How does supernova become black hole?
Supernova is basically a process, okay, where large stars, when they basically die, the end process is where they basically explode the outer layers. And the inner central region, that basically collapses and forms a black hole.
No, stop is closed. We don't start the talk now. Okay. Now, we have the council room. We have a few places to sit in the front on the ground. We have 2 or 3 chairs left. I request some of you are standing to go there. The rest of you can also go to the pandal if you want to. If you're here because you need to ask questions, we will not take any questions till the end of the talk. So that means you have to stand here till the end of the talk. Okay. Now it's also set up in the pandal now. They tell me that everything is ready, so we can start now. Yogesh, okay. Good. So it's always joyful for any person doing outreach when we have a large crowd. I think this crowd is a bit too large for us to handle, given that we are a fairly small institute. I'm really happy to have so many people here to visit us on open day, and especially to hear SanvedKolekar talk about what is a topic which everybody loves to hear about. Like I said again, there is a fire safety issue, so please do cooperate with us as well. We're very happy to have SanvedKolekar here to give us the talk on black hole shadows. Sanved did his PhD in Ayuka in Pune with T. Padmanabhan, who some of you might have heard of, the very famous Indian physicist who passed away a few years ago. Sanved did his PhD with him on theories of gravity, both Einstein theory as well as alternative theories of gravity. After which he spent a few years being a postdoctoral fellow in the UK and China as well as France for quite a few years. He is now a faculty member here at the Indian Institute of Astrophysics, and he works on theories of gravity, black hole physics, black hole thermodynamics, as well as quantum field theory on curved spacetimes. All of this sounds very fanciful, but all of these are something I know all of you are here to understand about, because that's what brings you here. And we're going to have Sanved here explain all of these fairly complicated terms in very simple ways for all of us to understand well. Therefore, Sanved, please go ahead.
Yeah, okay. So thanks, Neeraj. Yeah, thanks, Neeraj, for that introduction. So for the past few hours, I have been talking to a lot of people who have come here. So my voice is a bit fatigued, okay? So please excuse me for that. Yeah.
I'm really sorry. We just have 10 seats in the council room, 10 free chairs in the council room. We just got 10 seats for you. So please, 10 of you, please do go there. That'll be really helpful. Plus, there's space for the kids to sit on the ground, on the floor, they sit on the table. We don't care, just perch yourselves where you can. Yeah, we'll bribe you with, no, if you want a seat, then yes. Sorry, Sanjay, please continue.
So let me ask you this question. How many of you have already seen this image before? So was it in a newspaper?
Yes.
No.
Okay, so where did you see it? So you heard it when we announced the open day? Or was it before you heard of this open day talk? Okay. So what is that picture of? Like the title is already there.
This is a black hole reflection of a black star.
Yeah, so this is basically an image of a black hole which was taken by the Event Horizon Telescope. So the main aim of this talk is basically to understand how that image came about. Okay, but before we do that, we have to first understand what are black holes. Okay, what are the features and characteristics of black holes? Okay, why they have some certain peculiar characteristics. Okay, then we'll go to understand how they form. Okay, how do we know they really exist? Okay, what are the things that have been discovered so far about black holes? And then we'll basically go to understanding how they form this image. Okay, so yeah, so I'm basically a theoretical physicist, so I basically write equations. I'm not good at drawing things or making videos. So all the pictures and videos which you see in this talk, they have to be there because this is a public talk. So the credit goes to the people who have basically made them. They are not created by me. So this is just to say thank you to them. I have not captioned all their names when I basically took the images from different websites like NASA, from different journals, or even Google. Okay, so this is just a thanks to all the people who have created the videos and the pictures. Okay. Okay, so we'll start with what are black holes. Okay, so to first understand about black holes, let's first just understand a few things about Einstein's theory of general relativity. So before the theory, we all learned about, at least we have all learned in our school about the Newton's law of gravity, right? Two masses basically attracting each other. Okay, they have force of attraction, and we all know the formula. We have all used it. Okay, but Einstein basically said that no. Okay, that's not the ultimate formula to be used everywhere. Okay, that's not the theory which works everywhere. So we have to work with a theory of general relativity, and that had to come about because he had another theory of special relativity, in which he talked about the speed of light, the constancy of speed of light. So if you were to combine the theory of special relativity and Newton's gravity, then you get theory of general relativity. Okay, that was the main motivation for basically him. So that theory says that essentially gravity should not be thought of as a force. Okay, gravity is to be thought about as space-time curvature. Okay, so till now we have been used to the concept that whatever space we think about, let's say x, y, z coordinates, that is basically flat. Okay, but what Einstein said is no, that is no longer true. Okay, if you have, let's say, some masses, some energy, then it basically changes the background. The background becomes curved. Okay, and what tells how much it will be curved? It is basically the distribution of energy and matter. Let's say in this picture, you can see this is the picture of the Earth. So because of the presence of the Earth over there, the background has basically deformed. Okay, so basically space and time has curved. Okay, and in turn, the curvature of this space-time tells the particles which basically move on it how to move. Okay, so straight lines need not be straight lines; they might become curved because the background itself is curved. Okay, and this is the famous equation which he wrote. This is called as the Einstein equation. The left part is about the geometry, which basically tells you how the space-time should be curved, and the right is basically how the matter and energy is distributed. Okay, so now what was the original motivation? It was this basic simple experiment which Galileo did many years back. What he basically saw was that if you go to the top of the tower, and if you have, let's say, two masses, m1 and m2, and if you release them at the same time at the top of the tower, at what time will they arrive at the floor? So ignoring, let's say, the drag force due to air, if you just think about the force of gravity, both the masses, they basically arrive at the same time at the floor. Okay, that is because if you look at this particular equation, okay, the mass cancels on both the sides, so acceleration is just due to the force due to gravity. This we have all learned in school. That is why this is probably the only equation that I have in my slide. Okay, so this is not true for other forces. Okay, this is true only for gravity, because the gravitational mass which basically comes over here and the inertial mass which comes over here, they are the same. Okay, so using this property, Einstein thought about free fall experiments. Okay, if you have a lift which is basically freely falling, okay, then every object in that lift will also fall at the same rate because of this experiment, irrespective of mass. Okay, so they will appear as free fall. So using this idea, this whole theory was actually built up. Okay, so what are some examples of curved geometry? So this geometry we know. So this is, let's say you take just plain sheet of paper, you arrange it flat on a table. Okay, this is basically a two-dimensional space. Okay, it's a flat space. Okay, but let's say if you take another sheet of paper and form a cone out of it. Okay, or you basically look at a saddle which is there on the back of a horse. Okay, these are all two-dimensional spaces. Even this sphere, if you just look at the surface of the sphere, it is still two dimensions. Okay, so these are all examples of curved geometry. Okay, so basically his idea was that when you have energy and mass, the background, space and time, it is not just the space. So space is basically just the spatial directions, but you also have a time. So he said time should also be thought as a fourth extra dimension, which should be at par with the other spatial dimensions. Okay, he combined all these three spatial dimensions and one time dimension, and he called that as the space-time. And the theory says that due to the distribution of mass and energy, the background space-time will be curved. Okay. Okay. So this is the usual experiment which is shown like everywhere if you have been to some science centers or planetarium, that if you basically take a rubber sheet, okay, and then stretch it over here so that it is basically flat, and then you essentially send some object which goes in a straight line. Okay, something like this. But now if you put a heavy object on top of the rubber sheet, what happens is it basically bends over here. Okay, then if you try to send some object in a straight line, now what happens, because the background space is basically curved, the straight line will automatically look bent. Okay, so it will mimic the effect of gravity. So instead of saying that gravity is a force and something attracts, okay, you say that things basically move in their own respective straight lines, but because the space is curved, things appear to be bending. Okay, and this is the same picture over here. So for example, let's say if our sun is placed over here and we are looking at some star which is in the background of the sun. Okay, you can look at it only when there is basically an eclipse. Okay, otherwise the sky would be too bright to basically see the background star. But during an eclipse, you can perhaps see the background star, but you will not see the true position of the star. Okay, because what would happen, the light which is basically emitted from the star, because the space and time around the sun is curved, this straight line will actually be bent because of the background curvature. Okay, so if you trace back that line, okay, the projection which you see in the eye, okay, the position of the star will be not at the actual position over here, but it will appear to be shifted over there. Okay, so this is another feature of because of the curvature of space-time. Okay, now there is just a caveat that this analogy, one should not think that this bending of the rubber sheet is because there is essentially gravity which is acting downward over here. So this was just an analogy. Okay, in general, when we basically look at this diagram, it is that the space-time in general everywhere around the sun is in general bent. It is not a specific direction in which there is a dip below. Okay, so this is just an analogy to basically picture what might happen in a curved space-time. Okay, yeah, In fact, if you were to plot the, let's say, the path of a planet around a star, okay, in the space-time, then it would not look like a circle. It will actually look like a spiral because it goes ahead in time. Okay, so you have to think of all the dimensions combined and think of them as a quantity space-time. Okay, now they bring along some special properties. Okay, like depending on what the how it curves. Okay, you can have, let's say, two parallel lines which start to intersect. Okay, or you can have two initial parallel lines which basically diverge depending on the curvature. Okay, so you will have very nice general properties when you talk about curvature. Okay, so there is a quantity called as the curvature tensor, which basically captures this effect of how much the background space-time has curved. Okay, then the usual theorems which we studied, like the sum of the angles of a triangle, which is 180. Okay, it only works in a flat space-time. When you go to a curved space-time, that is no longer true. Okay, like for example, if you try to draw a triangle on the surface of a sphere, then the sum of the angles of the triangle will be larger than 180. Okay, or if you try to draw that on a hyperboloid, which is this particular picture, it may turn out to be less than 180. So certain theorems, Euclidean theorems, which we are used to, they will not essentially work. Okay, yeah. So the feature which I mentioned, that because the trajectories automatically get bent, they appear to be bent because of the background space-time curvature. So this feature was actually used to verify the theory of general relativity, which basically this person Eddington, okay, he was a professor in UK. He basically went in this 1919 solar eclipse time, okay, where he basically observed the change in the position of the star. Okay, and he found the particular number, and that number was close enough as predicted by the general theory of relativity, and basically he said that yes, this theory is true. So this is one of the tests of general relativity. There are likewise many different tests. Okay, why I came to this example is because when we talk about shadows, we will be basically talking about this bending of light. So this is just an example to warm up. Okay, yeah. So now, if you use the general theory of relativity to ask how does the background curvature look like for different objects, okay, let's say for the sun, okay, then you will have different types of background curvature depending on the mass. What is the distribution? So a sun, if you assume it to be perfectly spherically symmetric body, then it will give you a particular curvature. Okay, if you assume it's basically an oblate, something like an ellipsoid, like an egg, okay, it will give a different type of curvature. So basically, the theory tells you the different solutions. Okay, so in those solutions, there was a very particular solution. Okay, that particular solution said that if you take a perfectly symmetrical body, okay, spherically symmetric body, just like a sphere, okay, a ball of sphere, okay, and if you arrange the mass of the sphere such that, okay, it is connected to the outer radius of that sphere. Okay, if there is a relation between the total mass of that object and the radius of that sphere, okay, and it is such that if the object is smaller than this particular number which you calculate, okay, which is related to the mass of that object, then in this formula there is this Newton's gravitational constant coming and the speed of light. Okay, this is basically expressed in terms of mass of the sun. Okay, so for example, if you compress the whole sun, okay, within a radius of 2.95 kilometer, then it will do something peculiar, and that peculiar object is basically a black hole. Okay, and a black hole will be such an object that the curvature around it will be bent in such a way that if you now try to basically put light inside a certain radius, which is given with this particular formula, if you put light inside it, then it will never come out of that radius. Okay, so anything which is outside this radius, it is fine. You can maybe try to get it back. But once it crosses this particular radius, then you will not be able to get it back. Okay, this is true only if that body, the radius of that body is smaller than this particular radius. Okay, this is also called as the event horizon radius. Okay, or the Schwarzschild radius. Okay, now this is true for a spherically symmetric body. But in general, like somebody asked whether there are spinning black holes. So yes, there could be spinning black holes. Okay, so spinning black holes are called as Kerr black holes. Okay, then you can also have electrically charged black holes. So I'm sure you must all know about electric charges, right? So if you can also put electric charge on a black hole. Okay, then that formula gets modified, the solutions get modified, okay, and then you can even obtain the new event horizon radius, but the property is still the same, okay. If the outer surface of that body is smaller than which is given by this form, which is dependent on only three parameters: the mass, the spin, okay, which is in J, and the electric charge Q, okay, then you cannot have anything which escapes that radius, not even light. And light being the fastest body, anything else cannot move even faster than that. So whatever goes in must always lie within that surface. Okay. Another way to think about it is this. So suppose you have some particular object, okay, you are standing on surface of some particular large body, okay. So if the mass of that body is, let's say, some m, okay, and you throw that object up, so depending on that m, you will see that the body goes to a certain height, okay. But if you keep on increasing the mass, okay, then you will see that the height towards which this object goes will become lesser and lesser, because massive the object, more will be the gravity, okay. So similarly, the black hole is defines a radius, okay, where the force of gravity will become such a large quantity that if you try to throw something out, it will not even go up, okay. So you can imagine the black hole to be something like this. Try to throw objects, and how much force is required, that force would be actually quite infinite. You would require like infinite amount of force to actually come out from that particular object, okay. Yeah. So this is the same picture. So for the simplest black hole, which is the spherically symmetric black hole, like I said, this particular radius will be the event horizon radius, okay. That will be the boundary, okay. And then for objects outside, if you try to throw things up, I mean, they can basically move out, okay, because things, the light can come out from this particular point, and the escape velocity will be less than that of light. But at this particular location, the escape velocity required will be exactly matched to that of light, okay. Once you go inside, then you would require an escape velocity which is larger, which cannot happen with any true real particle. So things basically go in. Now this particular solution also has this feature, which also many of you have asked, like what is the singularity? So there is a point at the center where basically all the mass of the black hole has gone and sat, okay. So it's a point which has basically infinite mass density or energy density, okay. So that's actually not a physical point, because in the real world you cannot have something which is sitting in basically a zero volume point, okay. So like I said, the theory of general relativity will not work exactly at this point. So you would need to invoke some different theory along with general relativity, which is basically quantum mechanics, which basically deals with very small scales, okay. How to basically talk about things which are moving at very small scales, okay. And we right now don't know how to combine these two theories together. So this is still a mystery, okay. Now there is another peculiar property, that if something enters this surface, okay, this event horizon, like I said, it cannot go back out, okay. But there is another compulsion to it. So once it enters this surface, it has to go and hit this singularity. It cannot stay at any particular point. It cannot like go around in some circular orbits and stay there forever. Such orbits are not allowed, okay. It even cannot stay static at one particular point. No matter how large you have a rocket with you, how much, however large force you apply, okay. The property is, if you once enter this surface, you have to go and hit the singularity, okay. So basically, you can think that any particular mass, any particular energy, anything what you throw in will go and hit the singularity, okay. So the questions which were asked, like what happens to matter or things which are thrown into the black hole, what happens to them? So right now, all that we know is everything goes and hits the singularity. What happens after that, we don't know. Because if you want to look at trajectories beyond singularity, we cannot solve them using this theory, because the theory itself breaks down at this particular point. Okay, so we don't have yet an answer to that. Yes, so this is the singularity which happens in a black hole, but there is also a different kind of singularity which you must have heard, which is the Big Bang singularity. Okay, that is the kind of singularity which we basically say that has happened. That is the start of the universe. So because our universe, we know right now, is expanding, if you go and let's say look at it in the past, or you reverse the time, then everything will look like shrinking. Okay, so the universe will basically shrink, and then it will go and become a single point. Okay, so that will basically correspond to the Big Bang singularity. So that's a different type of singularity. okay, than this singularity. Then there are different type of other singularities depending on what is the type of black hole we are discussing. So this is the singularity which comes when you have a spherically symmetric black hole. So one person asked what happens when there is a spinning black hole. So when there is a spinning black hole, the interior structure also becomes different. Okay, this basic structure also becomes different. Now instead of one horizons, there are two horizons for a spinning black hole. Okay, and the nature of the singularity is also different. So that is basically like a ring singularity. So I didn't expect this question to be asked by some kid, so I didn't have that slide in my talk. But your questions are particularly advanced. Okay. Okay. So what are the other interesting features of the theory of general relativity? So one is the time dilation. Okay. What it says is, so this also is true, let's say for planets or above the sun, but there is something special which happens for the black hole. So what first happens for the planet? So let's say on the surface of the earth, you go at some height, you put a clock over there, and at a higher height, you put another clock over there. Okay. Let's say you start the clocks at the same time. Okay. So over here, they are, let's say, starting at maybe when this hand was at 12 o'clock. Okay. And then you wait after a sufficient amount of time, and you see this clock which is at the higher height. Okay, it has shown 30 minutes. Let's assume this is 30 minutes. But then the clock which is over here, which is at a lower height, it will only show 15 minutes. So basically the rate at which clocks run in a gravitational field, it's not the same. Okay, they will run at different rates. Okay, and that is because the strength of gravity is different at different locations. Okay, at this height, the strength of gravity is different than over here. Okay, so because of that, the rate at which clocks run, they are actually different. So the stronger the gravity, slower they run. That is the general thing. Okay. So a similar thing also happens for the case of the black holes. Okay. The closer you go to the black hole, the stronger the gravity. Okay, and it will be the highest at the event horizon. So if you arrange, let's say, a set of clocks, let's say in a line, okay, at different radius, then you will see that the clocks which are closer to the horizon, they will be running slower compared to the ones outer it. Okay. And if you try to put a clock exactly at the event horizon, which is not possible because the black hole will basically eat it. So just outside it, you will have a clock which is running very slowly. Okay, if you put it just outside the black hole, and somehow you manage to hold it. Okay, you just cannot put a clock there and just assume that it is going to remain stationary. It will obviously fall. Okay, so you would have to go and basically hold it stationary by some mechanism. Okay, so this is basically the time dilation effect. Now, the converse to it is the gravitational redshift. Okay, so suppose you have, let's say, some light, okay, and you are emitting it. So let's say you have a torch or a laser which emits light at a very particular frequency. Okay, let's say the green light or the red light that has a particular wavelength. Okay, and let's say you go towards close to the black hole and emit it outwards. Then by the time that the basically light ray has come outside, you will see that the wavelength has essentially decreased. Okay, so it becomes red shifted. So that is the terminology. It doesn't necessarily mean that it will always be red. What it means is it becomes lower in wavelength. So that is the terminology which basically people working in this area use. Okay, the other way is when you send something towards the black hole. So if you send a light of a particular color, okay, let's say the red color from outside towards the black hole, then it will basically become bluer. Okay, it will gain energy and it will become higher in wavelength. Okay, so that is called as blue shift. Okay, so this is an effect which is actually converse to the time dilation effect. Okay, now similar thing also happens in a black hole because of extreme gravity near the event horizon. What would happen? Basically they become like very high blue shift. Okay, or something which is emitted right outside the horizon of the black hole. By the time they come out, they will be like extremely redshift. Okay. Now there are other effects like the tidal effect. Okay. So in the tidal effect, what happens if you are, let's say, far from the black hole, and let's say you take a moderately sized black hole, not like a very large black hole, because to see tidal effects, you need, let's say, moderately sized black hole. Then if you move closer and closer to the black hole, let's say you are falling into the black hole, then your shape will not remain the same because of the different tidal forces which basically act on you. So what will happen is, first of all, your height will become more and more. So if you are falling feet first into the black hole, then the distance between the top of your head to the bottom of your feet, that will just go on increasing. Okay, whereas basically your waist size will become slimmer. Okay, so you become slim, but you will be tall due to the height. Okay, so the closer you go, this effect will be more pronounced. So this is basically the tidal effect. So this effect is also basically causing what is called as the rupture of stars. So if any star which comes near a black hole, the whole star will not remain like a star until it crosses the horizon. Because of these forces, you can imagine that the star will become elongated in this same way, right? From the feet and head, whatever you identify for that star, and the transverse directions will be squeezed, whereas the other perpendicular direction will be elongated. Okay, so basically it will be ruptured. So any particular object which goes towards this moderately sized black hole, it will basically, the shape will be destroyed. Okay. Okay. Now another peculiar property is black holes don't remember about their origin. Okay. So the solutions of black holes, they are described by only three parameters. Okay. One is the mass of the black hole, one is the spin, okay, J, and another is basically the electric charge. That is all it can remember. Nothing else it will remember. So what I mean is, suppose you basically take some mass which is made up of, let's say, this table, okay, and in other case you take something which is made up of some other material, let's say tea and coffee, and you compress them, you make them come inside that small Schwarzschild radius, you form a black hole. Okay, once the black hole is formed, it will only remember this mass of the total system it began with, or the charge, or the total angular momentum, which is the spin. It will forget everything else. Okay, so it will not remember how it was formed, whether it was formed, let's say, due to the collapse of some particular type of particle or another type of particle. Okay, so this is basically called as the no-hair theorem for black holes. Okay. Now this effect, okay, Hawking radiation, this cannot be just described using general relativity. Okay, you have to use some quantum mechanics. But whatever quantum mechanics or quantum field theory which you are using it near the event horizon. You are not using it near the singularity. Okay, so this is still not quantum gravity. Okay, what you are essentially doing is you are treating the background space-time as described by Einstein's relativity, but you are just putting some quantum mechanics on top of it. Okay, so what the statement is, as discovered by Hawking, is that what we have learned so far, whatever goes into the black hole, it never comes out, right? But still, a black hole alone on its own, or even if it is eating some material, it will still continue to emit some radiation. Okay, and that radiation is called as Hawking radiation, and that radiation is thermal, so it will have a temperature, and that formula for temperature is actually given over here. So it has like constants which depend on the same constant. Then it has the Boltzmann constant, it has the Planck constant. So this is basically a formula combining lots of different theories of physics, okay, which come together. So this is basically a number. So as we can see that if the black hole is of the mass of the sun, then the temperature is like 10 power minus at Kelvin. So it's really a very small temperature. Okay, so it's like a very small temperature. So if you want to have, let's say, a large temperature, then you need to have a very small black hole. So the formula is inverse of the mass. So smaller the black hole, higher will be the temperature due to the Hawking radiation. Okay, larger the black hole, this will even go down. Okay, now why does it happen? So actually there is a very nice way to look at it. So what really happens is, see, even in the vacuum around us, okay, if you go to any, let's say, a region of space where there is nothing there, okay, quantum mechanics tells you that out of nothing, there could be a pair creation which happens instantaneously. Okay, two particles being created, particle, antiparticle, and then they again merge and go back to vacuum. Okay, so there is basically an energy violation. Okay, because you can't create energy randomly, energy must be conserved. But if you have vacuum, you have zero energy, but when those two particles are created, there is some energy of those two particles, right? But quantum mechanics allows for violation of energy conservation only for a very short time. Okay, that is why they have to again merge and go back to vacuum. So you start from nothing, end with nothing, but in between you can have these two particles. Okay, but now because there is a black hole and there is an event horizon, if this process happens very close to the event horizon, it may happen that out these two particles which are created randomly out of vacuum, if one of the particles accidentally goes inside the event horizon, then they cannot combine again. Okay, so whatever is left, actually that comes out as Hawking radiation. Okay, so this is like a pedagogical way of understanding how does it work. So it requires quantum mechanics. You need to have that pair creation out of vacuum to understand Hawking radiation. Right. So these are basically the properties. Right now, what I have told you is because of the solution. So when you solve Einstein's theory of relativity, general relativity, the solutions, that is what you get. But the question is, do they really exist in our universe and how do they form? Okay. So we know such a process. So that has to do with the end life of stars. Okay. So basically, stars have this nuclear fusion which goes inside the central core, right? It basically generates this large amount of energy photons which are basically going outside. It has basically a high temperature, it has pressure, right? So whatever is the mass of the star, its tendency is to basically collapse due to the force of gravity. Okay, but this fusion process, it generates that whole temperature and pressure inside, which is radially outward. Okay, they try to basically push it outward. So there is always a competition between this mass which tries to fall in due to gravity versus this outward pressure because of the energy which is released due to the fusion. Okay, and because of that balance, the star remains stable and it continues to emit this energy. But this is not lifelong because the whatever is the source of that fusion inside, if it runs out of that fuel, that small atoms, basically small nuclei, become bigger nuclei. Okay, and to become a bigger nuclei to fuse, you need to reach some optimum conditions. Okay, like the mass should be sufficiently high for the fusion to start. Okay, so if that process by chance ends, okay, you can use up all the fuel inside the core. Okay, then this outward pressure is not there. Then basically gravity wins. Okay, so the interior portion basically collapses. Okay, so there are different ways in which basically the stars, right, depending on the masses. Okay, the outer layers of the stars, they may be basically thrown out very violently, okay, or not so violently. Okay, so you could have basically like a supernova or not a supernova, just a nova. So different processes are there. Okay, but it depends basically on the mass. Okay, so Chandrasekhar basically predicted this, that what should be the cutoff. Okay, so he said if the mass of the star is, let's say, around 1.4 mass of the sun, okay, then what would happen? Anything which is below this, it will end up in a white dwarf. Okay, it will not form a black hole. Some stars which are even heavier than that, massive than that, okay, till let's say 2.2 or 3, okay, roughly, then those stars at the end of their life, they will basically form a neutron star. Okay, but then stars which are heavier than this, let's say the 3 times mass of the sun, then they end up at this end of this particular process, then they will end up as a black hole. Okay, so it is balanced by this pressure. Okay, so there will be different reasons for that pressure. So you can see terms like electron degeneracy or neutron degeneracy. So these are again quantum mechanics which comes in, which tells you that it plays a role in balancing the force of gravity, which is inward. Okay, but these numbers are relevant. So what we found is the black holes that we tend to observe, they basically tend to obey these limits which were obtained. Okay. Yeah, so what are the other type of black holes? So this is the case for stellar type of black holes. Stellar, I mean, which have masses which are some factors times the mass of the sun. Okay, but in general, what we have found is there is also very large, massive black holes. Okay, these massive black holes are found at the center of, let's say, galaxies. Okay, and their masses are billion times the masses of the sun. Okay, so that is like 10 power 9 times the mass of the sun. Okay, so they can be that massive. Then there are intermediate black holes. Okay, which could be formed because there could be like many black holes which have come together in some central region. So there could be like a lot of stars formed in some central region which basically collapse. Okay, so this is not the only. This could not be the only reason. There could be different processes due to which this intermediate black holes could also be formed. Okay, but basically you can categorize them into these 3 categories. Okay, So what we generally believe is at the center of every galaxy, a large galaxy, there is basically a supermassive black hole. So that is the picture that we have. Okay. And this black hole at the center, it will be basically surrounded by a lot of things. So first of all, it could be surrounded by, let's say, the stars which are inside the galaxy. There could be a lot of material. Okay, there could be like a lot of gas, there could be a lot of plasma, which could be surrounding this central black hole. So what essentially happens is the material which comes in closer to the black hole, it will also have some orbit. It's not necessary that it will always be radial, because things always tend to move around the central object. So they have angular momentum. Okay, so as long as they have angular momentum, they will continue to move along. Only when they lose some energy, then they will go from a higher orbit to a lower orbit. Okay, and the way to lose energy is basically through friction. Okay, so there will be a lot of interaction between this material which is surrounding the black hole. Okay, they will basically rub against each other, slide against each other, interact with each other. They will become hot. They will release the energy in form of thermal radiation. They will lose energy. They will go closer and closer and ultimately fall into the black hole. Okay, so these are called as accretion disks. Now, not every central black hole to a galaxy has such a structure like accretion disk. Okay, like for example, our Milky Way galaxy, the supermassive black hole at the center of our Milky Way galaxy, it doesn't have such an active accretion disk. Okay, only occasionally some things fall into that black hole. But there are other galaxies like the M87 galaxy, which has a constant flow of such accreting material which goes into the black hole. Okay, so then you will have this region which is very luminous. Okay, so that's why in this particular picture you can see that the central part of the galaxy is appearing very, very bright compared to the other regions. So it is because of that accreting material is generating that much amount of luminosity, okay, which is around that black hole. Okay. So this is the same thing. So these are the this is basically a true picture. Okay, and this is just zoomed in. So this is an artist impression. Okay, so I can skip that. Okay, so this is the type of black hole that you observe. Okay, but let me just give you one proof. The first proof that the black holes basically exist and that existed at the center of our Milky Way galaxy. Okay, so they were basically discovered by these two people, Genzel and Guess. They did the observation of stars which moved around the central part of our galaxy. Okay, and the third person over here is basically Roger Penrose. He was given half the prize because he basically did a theoretical work to prove that when you have collapse of material, okay, when the star essentially collapses, you will end up with a black hole. So that was his theoretical proof much before in the 1950s, in the 1960s. Okay, and he basically showed that every time such a collapse happens in a black hole form, a singularity is inevitable. A singularity will always form. Okay, and his proof is quite general, so it doesn't limit yourself to, let's say, spherically symmetric systems or systems which have a particular shape or symmetry. Any haphazard way you collapse something, if it goes inside a particular boundary, the radius, then it is bound to form a black hole with a particular singularity inside. Okay, so for that proof, he was given the Nobel Prize. And these two scientists, they basically observed the tracking of the stars around the center of our Milky Way galaxy, which I'll basically describe. So yeah, so one point I'll just mention that in the proof which Roger Penrose mentioned or he proved, he used one of the theorems which an Indian basically derived, Professor Rai Chaudhary. So there is a famous equation named after him, Rai Chaudhary equation, which basically tells you how freely falling particles they move in a curved background in a very general way. So basically, Roger Penrose used his theorem to basically build his proof. Okay. Okay. So what was the technique that they used? So coming back to the Nobel Prize, 2020 Nobel Prize. Okay, they used something called as adaptive optics. Okay, so they were trying to look at this particular galaxy. So what is this picture of? Yeah, so this is the picture of the Milky Way. Okay, you can't see it from Bangalore because of the light pollution. You'll have to go to a very dark place to see it like this, even with the naked eye. You can see it with the naked eye if you're there in a really dark place. Okay, so somewhere in this Milky Way, you can identify where the center of our galaxy is. Right now, you cannot see it because there are a lot of things in the middle, in your way, right? There is basically dust, there are other stars, etc., etc. So you cannot directly see. So what they did was they looked at in some particular band of the electromagnetic spectrum, they looked at in the near infrared, which is the K band, okay, and they used a particular technique called the adaptive optics technique, okay, and using that technique, they basically looked at the center. So earlier, without that adaptive optic techniques, it looked like this. So everything was blurred. But because of that advent of that technique in those particular years, they started. So otherwise, the question would have been, why not the people in 1950 could make this observation? Okay, it was because of the advent of this technique in the later 90s that they could do it. So things become basically very clear. Okay, so yeah, so I'll just show you what they observed. So the number here basically says the year in which they recorded the position of the stars. So these are essentially the stars. These are the names of the stars. And let's just see how they move about. Okay. So remember, this is the year. So the star over there is that roughly marks the central point of our Milky Way galaxy. Okay. And then this is the motion of the stars about it. So you can see the orbit of stars which have completed full revolution. Like for example, this yellow one. Okay. So what does this shape look like? It looks like an ellipse, right? So basically the laws of gravity which we deciphered just by looking at the motion of planets in our solar system. Okay. The same equations they also apply to the center of our Milky Way galaxy, which is basically 27,000 light years away from us. The same set of equations basically tell how objects in the space they basically move. Okay, and they perfectly fit a particular trajectory. Okay, now it looks elliptical, but when it goes very close, obviously there will be some corrections due to general relativity. So it's not exactly ellipse, it is somewhat a little bit far from ellipse or a little bit closer to ellipse. Okay, however you want to look at it. Okay, so one particular case was this SO2 star. Okay, its time period was just 16 years. Okay, to complete one particular revolution around the central part. See, in comparison, the sun is also moving around the center of our galaxy. Okay, but the sun will take basically 200 million years to complete one revolution. So we are like very far from the center. So you can see how close this basically the star is. Okay, and this tells you the distance when it is at the closest approach. Okay, so it is just 17 light hours when it is closer to that particular center. That is how close that basically star went. Okay, and based on this computation, you can use your equations to figure out what should be the mass of the central object. Okay, using the formula for the ellipse, let's say, and that central object has mass of 4 million times the mass of the sun. Okay, and what is the order of size? So since you know what is the distance of closest approach, you can say that this whole mass is concentrated at least within that region. Okay, and what was the order of scale of that region? So from their observations, it was of the order of our solar system, around 125 AU. So 1 AU is the distance between sun and earth, right? So 125 times you can multiply that. So that to that order, this whole amount of mass was sitting. Okay. So what is the object that can be something like this? So if you basically punch in the numbers, it is very close to basically the Schwarzschild radius. It is not exactly the Schwarzschild radius. Okay. Because if the star was really close to the event horizon or the Schwarzschild radius of the central point, it would have been just destroyed. Right. It is still moving quite far off. That is why it is still intact to make one more revolution. Okay. So it is still far off, but just imagine that you have 4 million solar masses combined in the order of our solar system. So our solar system, let's say, is also 125 U with the sun sitting at the center. Now you take 4 million sun and try to like force them into this small system, right? You can imagine how large that or how massive that object is, which is sitting in a very small area. So it has to be a black hole. Okay, so that was basically the discovery. Yeah, so these are the same charts. Right. Now, this discovery was done in the early 2000s. Okay, if you noted the date. There was another Nobel Prize which was given in 2017. So this was given earlier but their discovery was actually done in 2015. So I have placed them in the order of discovery, not in the order of Nobel Prize. So what happens is there is a peculiar characteristic of general theory of relativity that we can have gravitational waves. Okay, just like if you have, let's say, a still surface of water, and if you disturb it, then you know that there will be waves on water. Okay, for example, this picture, you throw a stone in some on the surface of some still water, you will see some waves. Okay, similarly, because now gravity is being described as space-time curvature, okay, and not like a force, when you basically disturb it, okay, it basically creates waves. Okay, just like the waves on a surface of water. Okay, these are called as gravitational waves. So you need to have some central disturbance. Okay, so something like a very big explosion. Okay, that can also generate gravitational waves. Or for example, you can have, let's say, two black holes which are just revolving around each other. Okay, which could happen if you, let's say, had a binary system to start with, two very massive stars as a binary star. Both of them at the end of the life cycle, each of them became a black hole. Then they starting revolving around each other. So they will continuously emit this gravitational waves. Okay. So what was discovered was this gravitational wave. So we have gravitational wave detectors which can detect this basically waves. Okay. So that was done in 2015 for this particular object. Okay. So in that particular case, you had two black holes. Each of them were 29 solar masses, and the other ones were 36 solar masses. They basically spiraled around each other. They lost energy due to, let's say, the loss in the gravitational, due to the energy lost in the creating the gravitational waves. Okay. Then as they came closer and closer, they basically collided and combined and formed a larger mass black hole. Okay, 62 solar masses. Now the type of gravitational waves that it will basically create, this is the actual pattern which was observed in the gravitational wave detectors, in two different gravitational wave detectors at the same basically instant, to confirm that we are indeed looking at the same event. Okay, so depending on this wave, okay, which corresponds to this pre-merger phase, when the two black holes were basically rotating around each other, and then when they combined after the final black hole was formed, then you have a sudden dip in this frequency. Okay, this is basically called as let's say the church. Okay, so it basically, there is a particular signal through which you can identify the pattern in which this signal suddenly drops. Okay, that it is indeed a black hole. So just sitting in the lab looking at the gravitational wave detector, they proved that somewhere around in space, two black holes, they basically merged. Now they couldn't exactly locate it because you would need many detectors at different locations on Earth to basically exactly triangulate the position. Okay, so in their case, only two were running, so they could not exactly triangulate, but they knew that this process has happened. Okay, so this was another observation that yes, black holes basically existed. Okay, and that is why you have this particular signal. Okay, and this was so that is why this Nobel Prize was given earlier, because they were very sure that now yes, black holes exist, and only then they gave the 2020 prize, even though the discovery was made of the orbiting stars in the 2000s. Okay, so people were still skeptical whether black holes indeed existed, even though the other two people did their observations in 2020. Only when this confirmed it, they gave the Nobel Prize in 2020. Okay, so far there have been many such detections of gravitational wave mergers of black holes. So this chart basically tells you the same thing. So if you look at, let's say, two basically curves, you can see they merge and form a final black hole. So there have been many mergers which have been observed. Okay, so this basically gives us a window to look at the strong regions of gravity. Okay, because usually what would have happened around these black holes, if there are like lot of materials surrounding it, then you can't directly gauge things which are happening, physical phenomena which is happening close to the black hole. Okay, but now using this gravitational waves, you can go very close. You can understand things which happen close to the event horizon. So this is really a strong gravity region. Okay, so now coming back to the main question, like how does this picture basically form? Okay, so this is basically the black hole shadow. So we'll try to understand how this picture essentially forms. Okay, so first of all, what is this picture of? Again, the center of our galaxy, okay, which is around 27,000 light years away from the Earth. Okay, so the angular size that it subtends in the sky is same as if you go to the moon, keep an orange there and look at that orange from the surface of the earth. How small it will seem, that is the angular size. This basically central object, the central supermassive black hole will be. It is that small that we are trying to see with the Event Horizon Telescope. Okay. Yeah, so you have to zoom really in, okay, to look at the central structure. So let me just run a video which will tell you like how close or how deep that you have to go to look at the central object. We are zooming in. So you have to really zoom in. Okay, so what is the actual size of the object that we are looking at? Okay, so even though the mass of the central object is 4 million times the mass of the sun, the size is that just of the orbit of Mercury around us. So that whole thing, it will just fit inside the orbit of Mercury. That is basically the scale of that supermassive black hole. Okay, yeah, so now what creates that image? So we have to go back to understanding how the light is bent. Okay, so like I said, this is how the first test of general relativity was done, by seeing the shift in the position of the star at the back of the sun, okay, due to the bending of light. But this bending is only slight. Okay, like the number which I showed you, it only moved a little. But when you are talking about black holes, the gravity is really strong. Okay, so there the bending of light is very severe. It is very extreme. Okay, so yeah, so another instance where we also see this is when you have a cluster of galaxies, there is a lot of mass over there. Okay, so if you have some object which is even behind, let's say this cluster of galaxies, so you can have the light bending even in this scenario. Okay, but this also comes under, let's say, not very severe bending of light. This is still light. Okay, so the same picture, the same image of the galaxy can be seen in different directions. Okay, because you can have the light which comes over here, bends, comes towards you, then similarly from here, and then comes towards you. So you will see the same image of the same object twice. Okay, yeah, but for a black hole, the bending is so severe that actually light can get trapped in circular orbits around it. Okay, it can just go around a circle infinite number of times. Okay, provided if the radius of that circle is given by some number. Okay, so this is basically called as a photon sphere. Okay, so it is different than the event horizon. So the event horizon is given by the formula which I basically showed you. It's given as the Schwarzschild radius. There is a photon sphere which exists outside that event horizon. Okay, so that sphere is basically, let's say, a circle. It's a circular orbit over which if you put a light, it will just continue to forever remain over. So the bending is so severe that light also goes in a circle. Now this circle has a property that once the light basically crosses in, coming from out, then it can never go back outside of this circle. Okay, so it will always basically try to spiral in, and then ultimately it is caught by the black hole. Okay, but you can have things which are emitted from here pointing outward come out. Okay, so what I said is, if something is already moving in, if it crosses this particular circle or sphere, which is the photon sphere, then it has to move towards the event horizon. Okay, so this bending is again shown in the same geometric picture. Okay, so this is basically the photon sphere, and this is basically the event horizon. So you can have a set of trajectories, let's say light trajectories, which come in and then go around the circle, or if once they cross this particular photon sphere, then they have to go and fall into the event horizon. Okay, yeah, so now they can perform many times revolution around the black hole. They can actually come from far, they can go around once, they can go around twice, they can go around three, as long as they are outside that photon sphere. Okay, yeah, so to understand how shadow is formed, let's go back to how we know a shadow is formed. Okay, usually how we think a shadow is formed, so there is some object, there is a light source behind it. Okay, what we do is we draw these straight lines, okay, and let them fall on the screen. So you can see that this area will be dark because there is no light ray which basically comes directly from the source, okay, because of the object in between. So you see this is the shadow, okay. Similarly, let's say even in the case of solar eclipse, okay, the light from the sun is actually blocked by the moon, okay. So this is how you basically see the picture, right? Only the, let's say, some outer region which we called as the diamond ring, okay, depending on what is the distance of the moon from the earth, okay, then we basically see this picture. So it would seem to you that the black hole image is of the same type, like there is some source behind, the black hole is in between, okay, and the behind source is getting blocked because of the black hole, and that is why you are seeing that dark patch in between, okay. But no, that doesn't happen because for this picture, remember we drew only straight lines. So we said light moves in a straight line in these cases, but like I said, for black holes, light doesn't move in a straight line, it basically bends, okay. So even if you have, let's say, a source of light between you and the black hole, okay, a source not behind the black hole, even that source can act as sending light which goes behind the black hole and comes towards you, okay. So even that is possible. So what is the source? Like I said, the central black hole of galaxies, they will have this accreting material, okay, which basically emits all type of radiation. So now that is the source of light, okay. That light basically travels around the black hole in those set of trajectories and they come towards you, okay. That is the image that you will be seeing, okay. Yeah, so this is how essentially it will appear, that if you have, let's say, light sources coming from different regions, all the trajectories will be, you combine all the set of trajectories that you can possibly have and then construct the image over here. So let me run a video which basically shows you how that image will be generated. Okay, so this is basically the black hole. Now you had the light source from behind, okay, that light basically bent and then it came towards you. Okay, so this is how it will be projected on the screen. Okay, so this is for those trajectories which just went around the black hole. Okay, they didn't complete a revolution. Now this is n = 1, which means that those set of trajectories which at least go around the black hole at least once. Okay, so you can sort of combine all sort of trajectories. But also note in this simulation that the source is not just behind. The light is also coming from front. Okay, towards towards the black hole. It's actually revolving and then coming to the screen. Okay. So it's not just the source which is directly behind. The source could be anywhere. You just have to figure out those trajectories which go around the black hole and point towards you. Okay. This is the full combined effect. If you look at the total combined effect, then this is how the picture will appear to you. Okay. Right. Now, if you stare at this picture, it gives an impression that there is something going over the black hole. Okay, which is not true. So if there is a black hole around which there is an accretion disk, okay, just one accretion disk. So this is the front part of the disk which you are seeing. So this light is anyway coming to you straight, okay, but this part of the disk is actually not top of the black hole. It is on the back side of the black hole. But because the light from there has bent and come from over the top of the black hole, you are seeing the image of the back side of the disk on top of the black hole. Similarly, this particular part, it is still the back side of the disk which is appearing to you at the bottom of the black hole because the light from behind the black hole has basically curved and come towards you. Okay, I think this is the picture which you must have also seen in this movie Interstellar, if you have watched it. Okay, so it's basically based on this idea. Right. So now this is a black hole with the accretion material around it. Okay. So we'll see a movie how the image will be generated. Okay. If you are looking at it, let's say face on, okay, which means the disk is completely visible to you, then this is how the picture will look like. Okay. But if you change the orientation, then the picture of the disk will look a little bit different depending on how the orientation of the accretion disk is. Okay, right. So this animation also shows you one more thing. So let me run it again. So first it will tell you what is the real time image, actual that you should have seen, okay? But the way we take pictures is not a one instant click, okay? To make astronomical observations, you have to do a very long exposure image. So in the long exposure image, you will basically have such multiple real-time images stacked on top of each other, okay? Then obviously there will be some other issues, okay? You would have a lot of noise that would basically blur the picture. So instead of seeing that picture, you basically see this particular object. Okay, so it's because of the long exposure, blurriness, noise, which creates the picture like this. But you can see a central dark patch, which is the essential thing. Okay. Yeah, so this will tell you what happens on the inclination. So on the picture here, you can see how the black hole and the disk is with respect to you, and how the image will look like, okay, depending on the orientation. So you can see for face on and for edge on, the image is different. Okay, so how was this done? So basically, to look at such a small angular size, okay, you need to really have a very big telescope. Okay, so what they did was they actually cumulatively took observations from multiple telescopes, okay, distributed at many points over the Earth, okay, did simultaneous observations of the same central object, then combined the data using interferometry, okay, which basically effectively creates a telescope which has a mirror effectively the diameter as the size of the Earth. Okay, so it's not a full diameter mirror. So imagine if you had a big diameter mirror, but parts of it were broken, and you can take off readings only for small bits. Okay, that is what has effectively happened here. So you have taken reading from different small bits of that mirror, and then later combined it to generate that image. Okay, so that process is called as very long baseline interferometry. Okay, and these are the locations where the telescopes were there. Okay, and this observation was done in the radio band of the electromagnetic spectrum. Okay, not in the optical, it was done in radio, because apparently the radio signals which come from the central part, they are not absorbed by the material which comes in between. So like I said, there is a lot of dust and other things between the center of the galaxy and us. So anything which is emitted from the central part, it should not be absorbed. If it absorbs, then we can't see it. So we have to look for that part of the spectrum which basically bypasses that and reaches us to. So it so happens that that part of the radio spectrum, which is 1.3 millimeter wavelength radio waves, that reach us without being absorbed. Okay, so that is the one which we observe. So these are the set of radio telescopes. Okay, yeah. So this was the picture I showed you was for the center of the Milky Way, but there was another picture which was taken before that. Okay, that was for the supermassive black hole at the center of the M87 galaxy. That is even larger. So by this particular size, you can see that that is even actually larger compared to the black hole at our Milky Way galaxy. Okay, so this was million masses. This is actually billion times the mass of the sun. Okay, so this is basically like a chart. So the M87 star, the mass is about this. So you can see it is basically 6.5 billion times the mass of the sun. Whereas Sagittarius say our central Milky Way galaxy is only 4 million. Okay, even this is the difference in the radius. So this is like very huge. Okay, so the distance is from us around 55 million light years, whereas this is 27,000 light years. Okay, so even though it is like big, it is still very far from us. So it happened that the angular size in the sky for both of these are roughly of the same, not exactly of the same order, but roughly of the same order. Okay, that is why these two were targeted. Okay, so yeah, so these are other technical things. I think we have reached till 5:30. So maybe I'll just stop. This is just about the variability that since the supermassive black hole at the center of our galaxy doesn't have that accretion disk, you just have to wait for something to fall in, then it illuminates. Okay, so you have to take very long observations, like 8-hour, 9-hour long observations. Okay, so just imagine that in the dark, you are trying to take a photograph, let's say, of a dog which is running around. So you can imagine how the long exposure photograph will look like. It will be like very blurred. Okay, so that is what actually they did. Then they somehow actually stacked it together and recreated that image. Okay, and from there, how do you figure out the parameters of the black hole? Like I said, you have to figure out the mass, spin. So there is another way. What you have to do is you have to simulate that on a computer. You feed in a black hole with this particular mass, this particular spin, with this orientation. You generate the image of a shadow from there. Okay, you keep that as one template. Then you have another model of what should be the inner mass, spin, all possible combinations you do. You generate such a template, and then you match it with the actual image and statistically say which is the most likely template image which matches with the image that you have. Okay, and that's how you determine the parameters. Yeah, so this is how the images would be generated for, let's say, thousands of different cases which they basically do. Okay, and this is what they determine. So the black hole mass is around 4 million masses. Okay, which is same as determined by the looking at the trajectory of stars. Okay, they also figured out the same order. Okay, then what is the black hole spin? What is the orientation? So this is the best fit to the current scenario. Okay, so I think I will just stop here. Yeah, I'll stop here. Okay.
So I think we have some time for questions, and please raise your hand and we will keep the questions short. Yeah, so preference will be given, we have not asked questions at the beginning, so yeah.
Yeah.
Why is it not by objects which are numbers?
They have a lot of questions.
Yeah. Let's have the questions first because I think people also need to go home. Yeah. Right.
So you have mentioned about that the closer it is to the gravity, the slower the time will be.
Yeah.
So is it the stronger the time would be? So is it possible to time travel that way? It is slower and faster at the time.
So where do you want to travel? Do you want to travel in the past? That is not still possible, right? Because the clocks are just going slow.
Slower.
So you can't go to the past. You can always only go to the future. But you can decide at what rate you want to go to the future. Do you want to go slower? If you want to go slower, then go and live very close to the black hole, where the time will be very slow.
Yeah.
So you will live really very slow. You will live longer compared to the person who is staying very far from the black hole. Yeah.
Yeah, I.
Let's
Please, yeah, we'll take the questions.
Let me ask the questions and one. I request you. I definitely do this, but let's first just do the questions.
Those who have questions, please.
Please sit here, those who have questions, those who want to leave, please leave from the back door. Those who have questions, please be seated. We'll be taking, don't come.
Just because everyone is coming in. Yeah.
Please understand. Answer the question. Yeah, please sit, we'll take the question. Everybody has to do. Please sit, please. Will not take any questions.
What is nebula and why is it related with black hole?
So nebula is basically a remnant after an explosion, what you will see, right? So, yeah.
So, what is that red color round thing around the black hole? Is it light?
Sorry, which red color you are saying? This one?
Yes.
So, this is actually not red color. See, what we are observing is in radio wavelength. So that is some wavelength which we cannot see. We see these colors, right? Different colors. So that is called as optical band, like red, yellow. But these observations are not done in the optical band. So this is like a false image which is created. So once you take the image in radio, you give that particular frequency some color. Oh, this is the light. This is basically the radio light which is coming from around the black hole.
Yeah, next question.
Hi, sir. So the shape of the black hole, like with the accreditation, like how they show in the interstellar. So any point of the universe, if someone is observing, the shape will always be the same for them? And will the spinning of the black hole be any different for them?
So if you're talking about the image, depending on how you are seeing the disk, is it like face on or is it edge on? Then the image will change, right? Like I showed you.
Won't it be the same for like different viewpoint from the entire universe? Because it's ultimately it's a sphere, right?
For sphere, yes. For sphere, yes. But right now, what we are considering is also spin.
Yeah.
Because normally our galaxies and everything has spin, right? Angular momentum. So the black holes which we see mostly have spin. So they are like spinning. And these.
Depends on the plane on which.
Yes, yes. Then it also depends on the orientation.
Sir, so say you put charge. Okay, you put something in a black hole, and then when the black hole eventually like dies, what will happen to the information that went in, like the charge or the mass of the particle of the things that went in? What will happen to that after the black hole dies?
Okay.
What will happen?
Actually, you have asked a very, very important question, which I'm sure you might not have even realized at this age. So what you're talking about is the information paradox, okay, which Hawking realized. So like I said, black hole only has 3 parameters, and then it emits Hawking radiation. So Hawking radiation is thermal. So once the black hole, let's say, fully evaporates, let's say that is what is meant by the death of a black hole. So when it completely evaporates, you will be only left with thermal radiation, okay? And that thermal radiation doesn't know what is the original constituent which went into forming the black hole. Okay, so the information is yes lost. Okay.
Yes. But sir, doesn't that defy the conservation of information? It cannot be destroyed. What happens?
So right now there is no formula for conservation of information. Okay, that is there in quantum mechanics theory, what we call as unitarity. Okay, so it is basically a technical concept, and there is no conservation of information as such. But yes, information is lost because whatever has formed to become the black hole, that info is not there at the end of it.
But
Okay.
what about the thing? So there's a star with a certain charge, it falls into a black hole. What will happen to the information of the star, like the charge in the mass? What will happen?
So once it goes into the black hole, then it is lost forever for the outside world. That information is lost. So that is the information loss paradox which is associated with the black hole.
So I just can tachyons escape the event horizon?
So if tachyons exist, they move, then by definition they move faster than the speed of light. So then they can escape, but right now we have no evidence that they exist. Okay.
So in theory,
If they exist, they can escape the event horizon.
But did you try it?
Yeah, please.
How are they able to capture a clear image of the black hole, even though there are so many celestial bodies that are moving around in the galaxy itself? How did they know that this is the center of the galaxy? How did they know this is the black hole that is in the center of the galaxy when there is so much light water going on there everywhere?
Okay. So one area where we suspected where the center was, that can be determined by looking at the orbit of the stars. See, once I showed you that orbit of ellipse, right? So from there you can figure out where is the focus of the ellipse. Because at the focus, the central object should lie. So roughly we knew what region to look at. And then you need to use a selected band of the electromagnetic spectrum. So if you choose optical light to look at, then yes, it will be absorbed by the things which come in the middle, like dust. Okay, it can be scattered, absorbed. So you will not see what is inside. So you need that part of the electromagnetic waves which basically pass through all of this. And this radio light, okay, that does that. So that is why this particular frequency band was chosen to take the image.
Sir, here.
Yeah.
How hot is a black hole?
So it is given by the formula by Hawking. Okay. So for solar mass black hole, the temperature is very small. Okay. It's of the order of 10 power minus 6 Kelvin. So it's really cold. Okay. It is still hot, but it is really cold. Okay. Because the temperature is very low.
Can you see a singularity on its own?
Okay, so that is another good question. I don't know, the younger they become, the questions they ask are very hard. Yeah. So, yeah. So there is a theorem by Penrose, okay, the person who got the Nobel Prize. There is a conjecture by him, so which says that naked singularities cannot exist. If singularities occur in our universe, they must always lie behind the event horizon. Okay, so yeah, so if that conjecture is true, then they must always be shielded by event horizon. And a person who is outside the event horizon doesn't know what is inside the event horizon. Yeah. Okay.
While the black hole inside the Milky Way, I think there are many stars, so black hole is not
Yeah,
black,
go on.
black hole is not fit in that.
So yeah, so every galaxy at the center there will be a black hole because that is the region where a lot of mass is there. So that is the region where black holes can basically form.
Hello, sir, Lauren here. So my question is that how do humans, how did we discover that there's something called a black hole in the universe? What made us think that way?
Okay, so first we obtain the mathematical solution. So mathematical solution, you can say, yeah, mathematical solution was obtained much earlier in the 1920s itself. Okay, and then they realized that this solution is very strange because it would require the existence of an event horizon, which is like a one-way membrane, right? Everything goes in, but nothing comes out. Okay, then people really doubted whether such objects would exist. Okay, and then in the later years, when people studied about stars, processes of stars, then they realized that yes, there is a possibility that some certain physical phenomena could enter into a star. So the first proof was given in the case of, let's say, spherical collapse. Okay, not which is exactly spherical. Perfect symmetry. If you have, let's say, perfect symmetry and things fall inside in a perfectly spherical symmetric way, then it will form a black hole. So that was actually shown by this person Oppenheimer. So you have heard about him in a movie, right? That same person, he has a proof where he showed that spherical collapse will actually form a black hole. And then Penrose basically proved it that no, this special symmetry is not required. It need not be spherical symmetry. Even if you have, let's say, random distribution of matter, but somehow they basically collapse due to the gravity, then even without the special symmetry, a black hole could be formed and a singularity could be formed inside. Okay. And then the other part was when people looked at the center of such galaxies, they saw that they are like very active. Like there is a huge, there is basically this very big luminous objects or very high intense objects around them. So if you try to get an order estimate of how much energy or how much mass should be concentrated inside, okay, within that scale, then it turns out to be the order of scale required for a black hole to exist. So even during the time when Penrose proved the theorem, there were suspicions that this active galactic nuclei, quasars, okay, at that time that they were known, they should be like black holes which is sitting over there, which should be accreting things, and only then you can have such high luminosity coming from a very small central region.
So I have two doubts. So first one is that stars are also not perfectly spherical. They're a bit like,
Oblate.
yeah. So if a star collapses, assuming it's a uniform collapse, won't the black hole form also be oblate? And so my second doubt was that, like, in empty space, virtual particles and antiparticles come like for a brief second, and then they go out. So won't those particles exert some curvature of space-time? And since there are so many of them, won't they like influence something in this universe?
Okay. So for the second part, these particles are actually very tiny. So the background space-time curvature they generate is like hardly negligible. So I mean, it is just like a vacuum fluctuation. Okay, they are not that massive, neither do they have that much energy to generate that much heavy space-time curvature. What was the first question? Sorry, I forgot. Okay. So when spinning stars, they basically collapse and form a black hole. Then they will not form that spherically symmetric black hole. What they form is a spinning black hole. Okay, and spinning black hole geometry is not exactly spherically symmetric. It is called as axisymmetric. Okay, so yes, so it is not exactly spherically symmetric. Because of the spin, there will be some different effects which happen.
So how does Hawking radiation result in evaporation of a black hole?
Okay, so because you have this thermal radiation which comes out, it should be at the expense of something, right? So the only thing that black hole has is basically the mass or the spin. So it is extracting that energy to emit the thermal radiation from the mass and the spin of the black hole. So that goes on decreasing. Okay, and if you saw the relationship between the temperature and the mass, they were inverse. So once this thermal radiation starts, the mass decreases. It decreases, temperature increases. Okay, if the temperature increases, again mass decreases. So this is like a runaway process.
So is it generating the matter and antimatter at its expense of its
Yes, yes.
Oh,
Mass and spin.
so it's always lose half of its.
Not half. It will be dependent on what is the energy that Hawking radiation particle took up. It will exactly balance how much energy is extracted from the black hole in terms of mass and spin.
So, does the type of the black hole, whether it's spinning or stationary, does it affect the type of galaxy formed around it?
Yeah, so actually this is like an interesting question, whether the type of galaxy is because of the black hole inside or the other way around. So I don't think there is a clear-cut solved way to say whether it's the type of the black hole at the center which decides the galaxy how it should be, or it is the other way around. Yeah, I don't think this is still a solved problem.
So, can anything get out of a black hole?
Nothing else can come out, only the Hawking radiation which I mentioned, which is not exactly from inside the black hole, it is from near the boundary of the event horizon. Like I said, out of the particle-antiparticle creation and annihilation. So nothing comes out from inside the black hole. It will, if it continues to radiate this Hawking radiation, then the mass will decrease, right? And then the spin will also decrease. So then the corresponding Schwarzschild radius in the formula that will go on decreasing and decreasing. So it becomes smaller and smaller.
See, I cannot think beyond space-time curvature. I think it gets stuck there, what it means. So is there any equation of it, and if I take the time component out of that equation, would it be still a curvature or?
So see, the space-time curvature is both in terms of the spatial side and also in the time part. So it's not like when I say space-time is curved, doesn't mean the space part of it is curved. Even the temporal dimension, there will be a curvature even to that.
If I alter it from my equation,
Right.
and just keep the space, put it to the equation of the curvature or?
So if you basically select a particular time direction, that is what effectively you are saying. And then if you take an instant of that time and look at how the space looks like. So it can be curved, or it even, I mean, there are solutions where only the temporal part can be curved, but the space part need not be curved.
Thank you.
So thank you for a wonderful lecture, sir. As rightly said, the black hole will attract matter, the black hole lecture will attract the kids. So I have one question. You mentioned about the stellar black holes and supermassive black holes and intermediate black holes. Is it a kind of conjecture or still we have evidence to discovery of?
That is just a classification. Like you put the boundary somewhere saying that something below this will be the type of stellar black holes. Between this range would be the intermediate, and above that would be the supermassive.
Sorry. For calculation of all these, do we use Newtonian gravity or the relativity? Because I see in certain places Newtonian gravity getting used in some other scenarios.
So if you are really very far from the event horizon, then to the lowest order, your Newtonian gravity will still give you some answer, okay? But it will not be the exactly precise answer. For that, you will need general relativity. But if you are close to the event horizon, then you would need the full general relativity corrections. Like for example, the orbit of the star which I showed, see overall it looks like an ellipse. But if you try to fit it exactly with the equation of the ellipse, it will not work. So there will be some corrections to it. So lowest order, Newtonian gravity will be still okay.
Yeah, for sending all these to space and all, I think Newtonian gravity only is used.
Yeah, because here the gravity is like very
We
weak.
get a lot of precision.
Yeah, yeah. But this correction, so once you have clocks, once you send the satellites, now you have to do time sync. If you want to connect with some satellite, right? But that for that you have to use the time dilation formula. Otherwise, your clocks won't be synced between the on the surface of the Earth. Let's say some communicators on the surface of the Earth and the systems which you have in the satellite. So those are still corrected because of time dilation effects. Yeah.
Second question is related to you were mentioning about the quantum field theory and gravitational waves, right? So how are those?
Yeah, so the point was if you have to resolve or if you want to understand what the singularity is, see it's a region where there is very strong gravity, so definitely general relativity should be there, and you should use general relativity to describe something, but then the region is also very small, so then quantum mechanics should also be there, or quantum field theory. Okay, so then the point is you have to use both these theories together to describe something which is very massive, very strong gravity, and very small. But the point is we don't know how to use both the theories at the same time because they are like very different. So that's where the problem of quantum gravity comes. So do you have a theory which combines both the principles of quantum mechanics, quantum field theory, and general relativity, such that it can describe like what is exactly supposed to be at the singularity? So that we don't know yet.
Yeah, so maybe we'll take one question from each participant and then maybe we can have a discussion with them. We'll take last 4 more questions. Is that fine with you? Okay, yeah, go ahead.
Sir, first of all, thank you for the explanation. I would like to ask, why is it impossible to travel faster than sea? Faster than the speed of light? Why is it impossible?
Okay, so basically that is currently due to empirical things. Like we haven't seen any particle which essentially moves faster than the speed of light. Okay, and because of that, what we have done is we have built our theories surrounding this fact. So if you look at special theory of relativity, one of the principles says that the maximum speed of propagation of anything is the speed of light. And that is due to empirical evidence. So it is actually what observations tell you. That is what we are actually following. So if it was the other way around, then we will modify our theories to fit into the fact that yes, you can travel faster than the speed of light. But it's not observed. Like there is no particle which is observed which does that.
Theoretically, it is possible.
No, see, what do you mean theoretically? You define theories to match with the universe which you see, right? You can build an imaginary theory, but it will not represent our universe.
Yeah, hi, Kiran. Thanks so much for the information. So my question is, so much of matter is trapped into the black hole, There's some research done on where does it land?
So
much of mass and energy which is attracted.
Yeah. So it again
behind, where does it get it?
So it again comes back to the question of the singularity. So like I said, anything which crosses that event horizon, once it enters the event horizon, it is forced to go to the singularity. It cannot stay in between that region, between the singularity and the event horizon. It is forced to go to the singularity. Okay. And the point is, once that matter goes to the singularity, we don't know how to describe it further because all our equations fail when the trajectory has to pass to the singularity. If the trajectory doesn't go to the singularity, then we can evolve the equations. But our equations just fail when the singularity comes because the lot of divergences come, infinities come. So equations won't make sense if there are infinities. So the problem is still the singularity.
So whenever the mass are falling inside, so maybe if it gets destroyed, then afterwards when they are like emitting the Hawkins radiation. So the mass of the black hole will get small. So is it possible that when it changes from that radius, so if it gets more smaller, then all of it will explode out, or like some like mini Big Bang theory we can say? Is it like possible?
Okay, so that's a good question. So this Hawking radiation, the proof actually works for not for very small black holes. Okay, when let's say you have a very big black hole, when it becomes very small, then there is a problem called as the remnant problem. That when because there is a lot of information which has gone in, right, about the constituents, and what has come out is the thermal radiation, which doesn't have that information. So there is a paradox involved around it, which is the information loss paradox. Like where does the information go? So you can balance the energy. Okay, you can maybe let's say the whole black hole evaporates and you will have an equivalent amount of thermal radiation where the energy matches, but the information doesn't match. So we don't have a conservation law of information, but what we have is unitary evolution in quantum mechanics. Okay, that which basically says that probabilities are conserved. Okay, so it is another way of saying that you have to account for that information which is lost. So there is still a problem like what happens when the black hole becomes very small. Will the Hawking radiation continue to even work in that region when it is just about to evaporate, when it is at the order of the size of the singularity? Okay, so that's also still an open question. We don't know whether that process will continue till the full evaporation or it will stop at some particular point, then some other theory will be required to describe it. Because right now Hawking radiation is built on quantum field theory and general relativity separately. But at that small scale, again, you have to use quantum gravity theory. So maybe it can modify Hawking radiation or something else might happen. So that is still an open problem.
Can black holes make wormholes?
So wormholes are essentially, let's say, regions which connect two different regions of space-time together. Okay, so a black hole is what I described now. A wormhole is something else, but then people have tried to do the following, that what they have done in that geometry where the singularity exists, they have mathematically removed the singularity, taken another space-time geometry, stitched it up and said that look, something which goes into the event horizon, because now you have removed the singularity, you have stitched another space-time, the matter basically goes through there and then it enters that different space-time. Okay, but the stitching part, it's not physical because it needs to satisfy some set of equations for let's say real world physics to work. So it doesn't work. Okay, so I mean that is the only connection between black holes and wormholes.
Yeah, very good presentation by the way. In a chart that you have shown there, I observed a particular mass gap in the observation so far. There was a mass gap between neutron stars and a mass gap, and then the observed gravitational waves. I think it was gravitational waves. So, is there any reason, particular reason for that mass gap to exist? Okay, that is one thing, and also there is a paper by Sommerfeld Lab or Sommerfeld Center that primordial black holes, which you haven't mentioned. Primordial black holes is candidates for dark matter. So, is that research reaching anywhere or arriving at any point in the present time?
So for mass gap, see, one reason could be there is an observational bias. Like our detectors are sensitive to certain frequencies, and those sort of events which basically generate those type of with those black holes, only those are they have the tendency to be detected in our essentially models. So whether it is truly that in our universe those type of, or those band gap of black holes don't exist, is it true, or whether it's an observational bias, this is still to be resolved.
Will the proposed LISA project be able to observe those?
So for LISA, the actually the sensitivity is more towards supermassive black holes. But if it actually covers that range which you are talking about, then it may be possible. But see, even in that system, there could be an observational bias. So you never know. So to conclude it either way, we don't have enough information to go either way. Okay. And the other, what did you ask? So primordial. So the thing is, in the allowed range of masses which the primordial black hole should have, they should be of the order of, let's say, asteroids. Okay, the masses should be of asteroids, and there should be like uniformly distributed in the halo of the galaxy to account for that. So I think there are some still issues. So there are a lot of proposals which basically, so there are a few people in II who work on primordial black holes as a candidate for dark matter. But again, that proposal is not like very precisely done. So there are some even questions against that, that if you have such a distribution of asteroid size primordial black holes everywhere, then they could basically result in some other, like possibly constraint on other things like weak lensing data, etc., etc. So that is still not, I don't think that is still resolved.
Yeah, so we'll take last two more questions finally from him and then her. I think that's fine, right? Two more questions. Yeah, please go ahead.
So the images that we saw, the two images. So is the quality of those images limited by the fact that the telescopes that participated, those were terrestrial? So would we get better images if the telescopes were in space, like space-based observatory?
So if you improve the resolution, then obviously it will improve. Right now, since you are limited to put the telescopes on the surface of the Earth, so the effective diameter would be as of the order of the diameter of the Earth. But if you go to space and perhaps arrange this and make a large effective like baseline, then your resolution will improve and the image will also improve.
So what I meant is, can we take an image in different spectrum apart from radio?
Then the problem about the absorption and scattering comes in.
Even in space?
Yeah.
Okay.
Yeah, because it is not just because of our atmosphere, it is about also the things which are between us and the center.
Okay, yeah, last question we take from her.
Hi, sir. So when we saw the two black holes combining, one was given to be 29 solar masses and the other one was 36. But when they combined, it gave only 62 solar masses and not 65. It should have been 65, right?
So because it loses the energy in gravitational waves, so even if there is no matter involved, the lot of energy would be gone in terms of this gravitational waves. Also, sometimes depending on the orientation of the spins of the two black holes which are combining, if let's say they are not aligned, if they are something like this, then the resultant black hole can also get a kick. So I mean, it will not be in the same center of mass plane as the two black holes. It can actually effectively get a kick velocity because of the asymmetry of the system. So there are a lot of ways in which the total energy can be lost. So because of that, the final product is always actually lesser. It's not always like A plus B. Yeah.
Thank you.
Okay, then let's thank Dr. Sanved again for the amazing presentation. And thank you all for coming, and I hope you had a very nice time. So if you have any questions or you want any autographs, you can take them somewhere. I leave it to you. Yeah, thank you.
Thanks for receiving it. Heavy elements, right? But and black is like the only thing in the universe where everything compresses into one point.